Inside this vault is everything that matters. Your bank account details, your private messages, your medical records, the financial markets, the strategic secrets of governments. Every piece of data that defines our modern world is locked inside a digital vault like this. This vault is protected by a lock, but it's not a physical one. It's a mathematical one. A puzzle so complex, so mind-bendingly difficult that we believed it was perfect. If you took the most powerful supercomputer on Earth, a machine the size of a basketball court, and asked it to pick this lock, it would need to guess and guess and guess for 1,000 years. Some calculations put it closer to 1,000,000. We built our entire digital society on the simple fact that this lock is unbreakable.
We were wrong. This machine, it doesn't try to pick the lock. It doesn't guess. It follows a completely different set of rules. The strange, almost magical rules of quantum physics. In a way, this machine doesn't bother with the door at all. It simply walks through the wall. This is a quantum computer, and the revolution it brings will be the single greatest technological leap and the single greatest security threat of our lifetime. In this video, we will explore exactly how this machine is designed to break the internet as we know it, and more importantly, we will ask, what happens next? To understand the quantum threat, we first need to understand the lock. For decades, the gold standard protecting our data has been public key cryptography, most famously an algorithm called RSA. The name comes from its inventors, Rivest, Shamir, and Adelman. But the concept is what matters, and it's brilliant. It solves a fundamental problem of communication. How do you send a secret to someone if you can't first meet them in private to agree on a secret code?
RSA's solution is to create two keys. A public key, which, as the name suggests, you can share with the world. You can post it on a billboard. Bob gives his public key to Alice. He also gives it to anyone else who asks. The second key is the private key. This one, Bob keeps completely secret. It never leaves his possession. Now Alice wants to send Bob a secret message. She takes her message and uses Bob's public key to scramble it. This is the locking process. The scrambled message is now complete nonsense to anyone else. The only thing in the universe that can unlock and read that message is Bob's corresponding private key. Even Alice, who locked it, can't unlock it. Even Bob's public key, which was used to lock it, cannot unlock it. It's a one-way street. This is the magic. But where does this magic come from? It comes from a simple piece of math you learned in grade school: multiplication.
It is very, very easy to take two prime numbers, say 3 and 5, and multiply them to get 15. That takes a fraction of a second. But if I only give you the number 15, it is harder to work backward and find its prime factors, 3 and 5. This is called factoring. For 15, it's easy. You could just guess.
What if I give you the number 8,472,391? It's much harder. Now, imagine the numbers I use aren't 3 and 5. Imagine the prime numbers I use are hundreds of digits long. This is the heart of the RSA lock. The public key is that giant published number, the product of two secret primes. The private key is the prime factors themselves. The only way to break the lock is to take that giant public number and find its two secret prime factors. A classical computer is a brute force machine. It works in bits. A bit is a tiny switch that is either a 0, off, or a 1, on. To solve this factoring problem, it has to try combinations, one after another after another. It's like trying to find one specific grain of sand on every beach on Earth. This is the problem that would take our supercomputer 1,000 years. This is our unbreakable vault. Or so we thought.
A classical computer is like a light switch. It's definitive. A bit is either a 0 or it is a 1, off or on. All of its incredible complexity is built on that simple, rock-solid certainty. A quantum computer is not like that. It operates in a world of maybes. The fundamental unit of a quantum computer is a qubit. A qubit is not a switch. It's a possibility store. Thanks to a core principle of quantum mechanics called superposition, a qubit doesn't have to choose. It can be a 0 and a 1 at the same time. Think of it like a spinning coin. While it's in the air, spinning, it's not heads and it's not tails. It's in a state of both until you measure it. This is where the power explodes. If you have one classical bit, it can be a 0 or a 1. If you have 2 bits, you can represent 4 possible states: 0, 0, 0, 1, 1, 0, 1, 1. But only one of those states at a time. Now look at the quantum side. Because of superposition, one qubit can hold 2 values at once, 0 and 1. 2 qubits can hold 4 values at once. 3 qubits can hold 8 values at once. This is called exponential scaling. By the time you get to just 300 qubits, you can process more states simultaneously than there are atoms in the observable universe. This is the first part of the quantum key. A classical computer tries to find the grain of sand by checking each beach one grain at a time. A quantum computer, in a sense, can check every beach on Earth all at once. But how do you make all those qubits work together on a single problem? If they're all just spinning coins, how do you get a coordinated answer? This brings us to the second principle, the one that famously baffled Albert Einstein. It's called entanglement. Einstein called it spooky action at a distance. When you entangle 2 qubits, their fates become intrinsically linked. They are now part of a single, shared quantum state, and they will remain linked no matter how far apart you pull them, whether it's across a chip or across a galaxy. If you measure one entangled qubit and find out it's a 0, you will instantaneously know that its partner, wherever it is, has become a 1. There is no signal, no message sent between them. They just know. This spooky connection is the orchestra conductor. Superposition gives you an orchestra of infinite size. Entanglement is what gets them all to play the same symphony. It allows the quantum computer to coordinate its massive parallel calculation, with each qubit knowing what the others are doing. So we have a machine that can process a near infinite number of states at once, superposition, and a way to make them all work together on a single problem, entanglement. We are just one step away from understanding the attack. By the way, explaining these concepts is just as complex as the concepts themselves. If you're finding this breakdown valuable and want to see more deep dives into the technology that is shaping our future, take a second to subscribe to the channel. Your support allows us to build these complex explanations. Okay, we have the machine. Now, you just need the sheet music. You need the algorithm.
In 1994, a mathematician at Bell Labs named Peter Shor wrote the sheet music. He didn't have a quantum computer to run it on. They didn't exist. He just wrote the algorithm on paper, proving it could be done. It is called simply Shor's algorithm. And it is designed to do one thing: find the prime factors of a very large number. It is the perfect key, designed for our unbreakable RSA lock. We won't go through the complex mathematics of modular exponentiation, but here is the concept. You feed the quantum computer the giant number you want to factor. Thanks to superposition, the computer can essentially test a vast range of potential answers all at the same time. Shor's brilliant insight was to use a mathematical trick called a quantum Fourier transform. It's a way of using wave mechanics. This transform is designed to make all the wrong answers, the bad guesses, interfere with each other and cancel themselves out. This is called destructive interference. At the same time, it makes the signals from the correct answers build on each other, getting stronger and stronger. This is constructive interference. After the algorithm runs, this vast ocean of possibilities collapses. All the noise has been filtered out, leaving only the signal. And when we finally measure the qubits, when we stop their spinning and ask them to choose heads or tails, the answer that pops out with the highest probability is the correct one, the prime factors. A problem that takes a classical supercomputer, 1,000 years of brute force guessing. A quantum computer, using Shor's algorithm, could solve in hours. The private key is found. The lock is worthless. The vault is open. Every password, every bank transaction, every military secret, all of it exposed. This is the quantum threat, and it is very, very real. But this incredible power, it wasn't designed to be a weapon. It was designed to be a tool. This machine's true purpose isn't to break things, it's to build them. The reason it's so powerful is that it was designed to simulate the most complex system we know, the universe itself. The universe is quantum, the laws that govern how a molecule folds to create a new medicine, the chemical reactions inside a new battery, the atmospheric physics of climate change. Those are all fundamentally quantum systems. Our best classical supercomputers are just approximating them. They are guessing. It's like trying to describe a symphony by just banging on a drum. A quantum computer doesn't approximate. It is a quantum system. It can simulate these problems directly, qubit for qubit. It can speak the universe's native language. This means, in medicine, we can stop the guess and check of drug discovery. We can design new, perfect molecules from the ground up to cure diseases like Alzheimer's or Parkinson's, or to stop the next global pandemic before it starts. In materials science, we can finally understand and design room temperature superconductors. These are materials with zero electrical resistance. They would mean hyper-efficient energy grids, levitating high-speed trains, and a genuine revolution in power. In climate change, we can create catalysts that efficiently suck carbon dioxide right out of the atmosphere, or design new forms of fertilizer that don't pollute our planet. In artificial intelligence, we can train AI models on a scale we can't even dream of today, leading to breakthroughs in 100 different fields at once. This is the promise, a tool that can solve humanity's hardest problems. But to get there, we first have to survive the threat. So, this is the race we are in. A global race to build a quantum computer powerful enough to break our locks. And a simultaneous, desperate race to replace every single lock on Earth before that day comes. This isn't science fiction. This is happening right now. Cryptographers at organizations like NIST, the U.S. National Institute of Standards and Technology, have been working for years to develop and standardize post-quantum cryptography. These are new kinds of locks, new mathematical problems. They are built on different principles, like lattice-based cryptography, that we believe are hard for both classical and quantum computers to solve. Shor's algorithm, it doesn't work on them. The transition will be the largest, most expensive, and most critical infrastructure upgrade in human history. Every phone, every server, every car, every satellite, everything that connects to the internet will need to be patched.
The quantum revolution is coming. It is not a question of if, but when. It will be the single greatest technological leap and the single greatest security threat of our lifetime.
The challenge is to be ready for both. We want to know what you think. Which application of quantum computing, the good or the bad, worries or excites you the most? Let us know your thoughts in the comments below.